Welcome back everyone to this lecture discussion on cross-validation. Cross-validation is a more advanced set of methods for splitting data into training sets and testing sets. The relevant reading for cross-validation in ISLR can be found in section 5.1. As a quick note, later on in the course we'll have a much deeper dive and discussion into specific scikit-learn cross-validation capabilities. Right now we'll just have a general overview of the main concepts behind cross-validation, because many of the regularization techniques come with a sister class that actually performs cross-validation automatically for you for the case of hyperparameter tuning. So this is just an overview of the idea. Later on, we'll dive much deeper into scikit-learn's highly customizable classes regarding cross-validation. Now we already understand the intuition behind performing a basic train test split. That is, we want to fairly evaluate our model's performance on unseen data. Unfortunately, this means we're not able to tune hyperparameters to the entire dataset. We have to sacrifice a portion of that dataset in order to hold it back for testing purposes. So, is there a way we can achieve both of the following? Train on all the data and evaluate on all the data. While at first this sounds impossible, since it's paradoxical to train on all data and evaluate on all the data, we can actually achieve this by being clever with cross-validation. So let's have an overview of the concept that allows us to both train on all the data and evaluate on all the data. So we're going to imagine our data set that we've been working with. We have some features, we have a label. In this case, it's the housing data set. And what I want to do is convert this data into colored blocks that are typical for the explanation of cross-validation. But instead of jumping directly to those colored blocks, I just want to relate what those blocks are actually standing for. So what we're going to do is convert this to the generalized form. We have the features, we have the label. And instead of coloring based off feature and label, I'm going to color off of train versus test set. So select some of it to be a training set, select some of it to be a testing set, and then color them. And then for now, I just want to consider the idea of data for training versus data for testing. I'm just considering all the data, both the features and the labels. So let's go ahead and get rid of the labels or the column labels for X and Y. And right now, I'm just considering I have all this data colored by training set versus test set. And then the way you typically present cross-validation, visually that is you'll go ahead and rotate this, resize it, and then kind of flip it. So now I have my data, same data we've been working with before, and I'm just representing it as the full data source with the splits. Here blue is train and yellow is test. So now let's start with just all the original data. So I haven't actually split it yet. So how does cross-validation actually work? Can I be clever by getting a chance to train on all the data and evaluate on all the data? Well, what we do is we split the data into k equal parts. K is a number up to you to decide. Then you'll have 1 over k left as a test set, which means if you decided k is equal to 10, that means you're leaving 10% of the data, or 1 over 10, as the test set. And then what you're going to do is you're going to train the model and get the error metric for this particular split, where you maybe did a shuffle first, and then you had the last 10% as your test data. Then what you're going to do is you're going to repeat this for another 1 over k split, and then get a second error. And then you're going to repeat this for all possible splits, essentially repeating this k number of times. And so, after you've repeated this k number of times, and you've been able to both evaluate and test on all portions of your data just by running this k number of times, you'll average out the error. So here we get an error for the first split, second error, third error, get error equal to k, and then we just average all those and get our mean error. And the average error is then your expected performance. And what's really nice about this is it actually gives you a much clearer idea of the model's true performance, because you went ahead and evaluated the model at a certain point on every single piece of data. And you also tested every single piece of data at a certain point. So we were able to train on all the data and evaluate on all the data. The caveat being you weren't able to do it all at once, you had to do it k number of times. But what is nice about this is you get a much better sense of the true performance across multiple potential splits. So you might be thinking, what is the cost of this? Why don't we just always do cross-validation since it gives us all this information? Well, the issue is you have to repeat the computations k number of times, which can be computationally expensive for very large data sets. This is known as k-fold cross-validation. A very common choice for k is 10, so that each test set is 10% of your total data. So we would recommend by default, if you're going to do k-fold cross-validation, you choose something like k is equal to 10. Keep in mind that the largest k number of splits possible would be k equal to the number of rows. And this particular case, where you're going to go ahead and just draw one row as your test set, train on everything else, and then go on the next row as your test set, train on everything else, that's known as leave one out cross-validation. And as you can imagine, that's computationally extremely expensive, but it will give you the most accurate reading for your particular model since it's training on everything but one row of the data. And then you're going to average all those errors across all those rows. So that's known as leave one out cross-validation. Typically, for most problems, just using k-fold cross-validation will give you more than enough information. You don't need to go all the way to leave one out, but it is an option for you if you feel the need. One consideration to note with k-fold cross-validation and a standard train test split is fairly tuning the hyperparameters. So this is more of a philosophical problem with machine learning than it is kind of a mathematical or quantitative one. Let's imagine that we are running through the machine learning process, we train on our training set, and then we test on our test set, and we decide we want to go back and adjust hyperparameters. If we're tuning hyperparameters to the test data performance, are we ever fairly getting performance metrics on truly unknown data? If in fact you went ahead and tuned hyperparameters on that test data, to some degree you are letting a little bit of knowledge leak from that test data set because you're tuning based off those results. So in a sense, you're slightly cheating. Even though the model has technically never seen this data to be trained on, you are, as the data scientist or machine learning practitioner, going back and adjusting hyperparameters based off that test data. So are we ever actually getting fair, true performance metrics on data that's never been seen and never been, more importantly, adjusted to? How can we actually fix this problem? Well, if we want to understand how the model behaves for data that it truly has never seen and never been influenced by for hyperparameter tuning, what we do is we use something known as a holdout test set. And keep in mind, this is where the semantics can get slightly confusing because we're expanding beyond just a train test split. Instead, we will have a train, validation, and then a final holdout test set. So let's explore what this actually looks like. So what you can do is you start off with the entire data set. And then what you're going to do is remove a portion of that, and you're going to call it your test set, or more specifically, your holdout test set. And this is a set of data that the model will never see and also never be adjusted to. And so what you could do is perform a classic train test split that is something like a 70-30 split, and then you'll train and tune on that particular data set. Or what you could also do is, same idea, you'll just do a k-fold cross-validation instead, and then train on tune and that particular data. So you can adjust hyperparameters based off either the cross-validation train test splits or just a regular train test split. The main thing to note here is that little piece of purple data that we set aside, we never touch that data, we don't tune to it, nor do we train on it. So after training and tuning, you perform a final evaluation on what we're calling our final holdout test set. The very important thing to note here is that you cannot tune after this final test evaluation. The idea behind that being is you want some sort of performance metric as a final report telling you how well the model is going to perform based off data that it was not trained on and based off data that it was never adjusted to. In a sense, we were technically cheating slightly by adjusting hyperparameters to the test set. So of course, you would expect, after you keep adjusting those hyperparameters, to improve performance on the test set. But it's not really fair to then report those same performance metrics on the test set since you technically adjusted the model to that test set. So instead, what we do is we have this final holdout test set, and then we run our model on this final holdout test set, and that's what we're reporting as our true final performance metrics. And obviously, to make it fair, we're not going to go back and then adjust our model to hopefully perform even better on this data. Instead, we're using this final performance metric as just a report. So you can imagine if you have a boss coming in and asking you, how well did the model truly perform? You're going to report back this final number, and you're not going to tune after this. So the way this is then typically labeled is you have your training data, and your validation data is what you're tuning your hyperparameter to. And then you have this final test data that you don't get to adjust off of. Again, the semantics can be a little confusing here because the test that we're normally training and tuning on ends up being pushed out. So it's train validation test split, otherwise known as a train validation holdout test split or holdout data set. Don't worry too much about the semantics, worry more about the idea behind it, where this final holdout test set never gets tuned on. It's your final performance that you end up reporting. So we get a true final performance metric to report, and you do not edit or try to tune model hyperparameters after this. It's for the sake of getting true performance metrics from the model as honestly as possible. This is why it's kind of more philosophical than quantitative. So keep in mind, all these approaches are valid. You could, if you want, just do cross-validation, or just stick with something like a 70-30 train test split, or do cross-validation and keep that holdout test set. Things to keep in mind are, how was your previous modeling work done? Or is this a new model that no one's ever tried before? What are the reporting requirements behind your model, and how fair do you want the model evaluation to be? Is it fair to you and to your colleagues and your work environment that you're reporting test metrics on something that the model's been tuned to? Whether or not that's fair kind of depends on the context of both the data and the model. So lots of things to keep in mind. And again, this is where kind of philosophy starts mixing in of machine learning and the more quantitative aspects, because there is no 100% right answer over what's the best approach to take. The most robust approach, though, would be something like k-fold cross-validation with a holdout test set. Something to keep in mind is many regularization methods have tunable hyperparameters that we can adjust based on cross-validation techniques. In fact, it's so common to choose these tunable parameters based off cross-validation that scikit-learn has built-in cross-validation sister calls to the regular regularization class calls. And we'll see that when we actually program that out with scikit-learn. For simplicity, there are times in the course we're just going to opt for a simple two-part train test split instead of going all the way through cross-validation, since for a lot of this course, we really care about just learning and understanding and implementing models versus trying to get some true reporting metric, since we're not really doing this for any sort of reward or job. All right, with that being said, there's one more thing we have to do before we jump into regularization, and that's setting up our data. And that includes things like a train test split, as well as the feature scaling that we've already talked about. So we'll see you in the next lecture where we perform that data setup.